Here I have shown you a container, okay, in which you can hold up certain amount of water or any type of fluid, and it has an angle of theta with the y-axis as well. Okay, if I say that definitely it has a certain angle of theta with the horizontal surface. Now the matter is that here we are interested to identify the resultant force and its position of this particular surface, complete surface. Okay, we are not interested in bottom surface, we are not interested in that particular side surface, we are studying this surface. Okay, if we are able to resolve this surface, we can easily resolve that one as well, and the behind and front surface easily with a similar solution. So for the purpose of resolving this particular surface, if we want to resolve it in 3 dimension, the problem become more complicated as well, and the derivation become more complicated. So what we have done is, this is the 3D diagram, but we reduce this plane surface in 2 dimension in such a manner that I name this axis as an x-axis and this axis as a y-axis, which making an angle with a horizontal surface. If the liquid is filled up to that height, let's say completely filled, and it has a certain height with that part, so it making a triangle type of material. So for that we only consider these 2 axes in order to resolve our mathematical expression, in order to identify how the hydrostatic force exert on the surface of this plane surface. Okay, now we move towards our slides. Okay, and here you can see this is x-axis, this is y-axis, this is the front view of your container. From the front view, we only can see the y-axis. Okay, and we can see that it is filled up to that much level, and the y-axis, which I have told you, is making an angle of theta with the horizontal free surface of the water. Now if I want to determine the FR, let's say FR is present here, the height from the free surface to the point of the application of FR, we are saying that it is equals to YR. Okay, this is the y-axis, this is the origin point, and when we move forward to the position at which the resultant force is acting on this solid surface, we name this length as YR. On the other hand, if I say definitely this surface, this rectangular surface, which rectangular surface? This rectangular surface has a center of gravity point as well, at which the whole body weight concentrate. our whole body mass concentrate. This is the point which we so called as the center of gravity. So I name this as YC, okay, and if I am identifying the value of df, okay, we divide the forces in small testimonial sizes, so in which we can say that df is any variable, any force is applying on particular position, and the position can be the length of that particular force is variable, and we denote it as y-axis. The important thing to note is that this y, if I see the vertical distance, okay, for vertical distance, how I have to move myself? The vertical distance is something like move in that particular direction from position to the point of how much the water filled in that particular container. So if I am talking about the y point, the vertical distance is h. If I am talking about the center point of centroid point of the complete rectangular surface, I name is it in y-axis yc, and for vertical distance I am saying that it is hc. So I think it is now understandable to you to know how we have resolved this particular diagram in two axes, x and y axis, and we will utilize these values in order to develop a mathematical correlation between the resultant force and the position of the force in order to determine their magnitudes as well. The x-axis is not so much complicated. Definitely, if I am talking about the x-axis, so x is actually nothing, just a distance from this is the origin point, okay, and I am moving from this part to this direction. This will considered as the positive x direction. Definitely there is a point at which the centroid of this rectangular surface is lying, okay, so from this point to that particular centroid point, I am notifying that point as xc, which you can see here represented as this, and the point at which we don't know where it is actually, where the resultant force is exactly applying the force on a particular point, so we notify that distance with the origin in x dimension as xr, okay. So this is the whole diagram, and we can identify any type of as we resolve it in the form of pressure and force. So definitely there is influence of the area as well and the area as well. So now we move forward to our derivation part. If I need to determine the FR, what I will do is I will integrate df. Integration is something that we are sum up all the small forces which is applying on a particular plane surface, in that direction. So which will be equals to it will be equals to the specific weight to the volume. Okay, and how the volume is changing, so we integrate all the dA for a particular height, so we can easily understand what is the force present or the resultant force magnitude. So we did nothing if we know that from our figure that the back slide, as we can see here, H is equal to y sine theta. How? This is y actually. This is the distance y, which is making an angle of theta. This is the base and this is the perpendicular, and if I will say, considering this hypotenuse, this component can be written as y sine theta, and this component of y can be represented as y cos theta. So we can equate h is equal to y sine theta here. Okay, so we just insert the value of h in the form of y, so the equation become in that manner. Okay, and then we consider that the specific weight of whole container remains constant and the theta is constant for that particular plane surface, not a curved surface, it's a plane surface. So considering that these two becomes constants, and this is a factor come across to us, which factor is normally called as the first moment of area, and I have represent what its definition is. The first moment area is nothing, it is the sum of infinitesimal part of the shape of the area of that part times the distance of the axis, and which can be equated by the definition into yc times the area by the definition. Okay, so we what we have to do is we just put this value in this form, and we can easily identify what is the magnitude of Fr. So we need to determine the specific weight of the fluid, the area of the plane surface, yc distance, and sine theta. After that, we can easily determine the magnitude of the force, but we unable to even identify whether the force is applying on the centroid part or any other part. Okay, this is only for calculating the magnitude of the resultant force, or which can be simply called as y c sine theta is equals to hc. So vice versa, you can use this expression as well. Then we need to determine what is the position of at which the force is actually the resultant force is actually applying its magnitude. Okay, for that, what we have done is we utilize the moment arm equation, that the anti-clockwise is equal to the clockwise. So here is the Fr times YR, which will be equals to definitely all the forces applying to their respective positions. Okay, so this is force and it is force arm. So we are equating or summing up the moment arms. Here we know that what dF is from the previous slides. The dF is nothing. It is equals to sigma y sine theta dA. So we put this values in that equation. Okay, and as y is present, so this y becomes y squared. I forget to write here dA. So dA is also present here. Okay, so after this is our first equation, and we also determine Fr value as well, which is equals to this sigma a yc sine theta or sigma a hc. Here we are determining the yr position of the resultant force, so we want to resolve everything in the form of y variable. So here we will put our value of Fr in this equation. When we put this equation, the specific weight cancel out and sine theta just cancelled out, and we come up with this type of equation that area is present, y squared dA yc. Now again, this integration form is some so called as the second moment of area, which described as how uniformity present in the form of inertia within any body. We will not go in the depth of that, because I know you have studied all these course or topics in engineering mechanics, so just recall that. So this factor become Ix completely, and we know that Ix is nothing just equal to Ixc plus yc actually it is equals to Ixc plus area times yc square. When you put this value in this equation, it come up with this reduced form, that Ixc over yca plus yc. Why we reduce this in the form of Ixc? Because we can determine Ixc value. If we know the shape of the body, we can determine the Ixc values, okay, and we can easily calculate them. So considering that, we come up with a solution respectively. XR has similar formula for that. So by knowing XR and YR, you can actually understand where exactly the resultant force is present and applying force. And if we talk about the liquids, definitely its direction will be perpendicular to the solid boundary, so there is no need to determine the angle of the resultant force. These are different plane surfaces. Either they are circular in cross sectional, rectangular in cross section, or any other type of cross section. but we can determine their values in that manner. Once you have calculated the IXC values, you know the specific weights values and YC values and the area, you can easily determine the resultant force and where the resultant force is applying. After that, we have a numerical in which a large open tank contains water and it's connected with 6-foot diameter conduct as shown in figure. A circular plug is used to seal the conduct, determine the magnitude and direction and location of the force of the water on the plug. Actually, this is a huge reservoir of water and there is a downstream conduct or circular path passage available to flow water. Okay, but there is a plug which right now in closed form, so we need to determine at this cross-sectional area where the resultant force is applying and the magnitude of the resultant force. So for that, we again move towards our whiteboard. So this is the figure in front of you. This is the circular plug which is installed in the passage of water, which has a diameter of 6 feet, and I converted this 6 feet in meters, so it becomes equals to around 1.8288 meters and meters. I actually used to resolve the numericals in SI system. So what we need to know is the specific weight, the value of specific weight. We know area of this circular plug will be equals to A is equals to pi r square but here we have diameter, so d square over 4. We come up with 3.14 multiplied by diameter is 1.882 square upon 4, and the value will be equals to 2.625. 625 meters square. YC value. Okay, so YC from figure, SC is equals to YC, but it is equals to H1 plus half of D. So we can able to understand this part actually equals to B by 2. It is hard to visualize, but here I write here that YC equals to H1. H1 is the height of this whole 9 feet, you can see from the figure, plus D by 2. So which is equals to, if 9 feet is converted into meters, it has a value of 2.7432 plus diameter has a value of 1.8288 divided by 2. So YC is nothing, just equals to 3.65, meters. So this is the value of yc. So and theta is nothing, it is equals to 0 or 90 degrees. Here the angle is 90 degrees. So we put all these things in the equation. So Fr will be equals to the specific weight 9810 multiply the area which we have determined 2.625 yc value which is equals to 3.6576 multiplied by sine theta, sine 90 degrees. So Fr will be just equals to 94.187 newtons. On the other hand, if we are going to calculate the value of yr, we need to determine, we know what is yc, we know a, we know yc. Ixc is the value which we need to determine. For that we will go for our figure. Okay, here you can see the Ixc equals to 1/12 dA power 3. So I rub out certain part. Ixc equals to 1/12 So the plug has a circular passage. So Ixc is equals to yc, which is equals to pi r power 4 upon 4. So we will write this equation here in the whiteboard. Okay, pi r power 4 upon 4, and which come up with 3.14 multiplied by r will be equals to d divided by 2, and d is equals to 1.8288 divided by 2 and whole power of 4, and this is divided by 4. So these are the formulas which you need to determine in using all these factors. And here you can see the d divided by 2 whole power of 4. So Ixc will be nothing, just equals to if you calculate 0.5488 meter power 4. Now everything is known, so we just put the values. Ixc 0.5488 divided by YC. YC we have calculated as 3.6576 multiply by area. Area is equals to 2.625 plus YC again, and YC value is 3.6576. So YR will be equals to 3.715 meters. Important thing note, which is need to be noted, is YC is equals to 3.6465, and YR is not lie at centroid part of the plane surface. It's always below than the centroid part. So important analysis of through this numerical, we comes to know that the resultant force always apply below than the point present from the centroid. The centroid point is higher in position as compared to the resultant force application point on the plane surface.